in slightly varying lengths. So I want to kind of pick up where, or kind of finish up from where I was yesterday. And just to kind of briefly recap, I was discussing, I'm going to have three topics, and the first topic was linear optics, or linear response theory, and its application to various kinds of quantum materials. The next one is nonlinear optics and its application to quantum materials, and then I'll talk about quantum optics. So I want to finish up on the first topic, and I kind of gave a broad overview of kind of some of the general things that we could say from quite general considerations, right? So I emphasized a number of things yesterday. Well, one of the things I started with was emphasizing just, if you will, the experimental difficulties involved with understanding and characterizing materials at all, not just quantum materials, with optical measurements, right? So we're looking for natural frequency scales of various physical processes, and those physical processes run over perhaps 9 orders of magnitude easily from what we might want to characterize. And so what I'm going to talk about today is techniques, and you're going to see a little bit of that where we have to kind of have niche applications of various different kinds of experiments. I think it's important for theorists even to understand how experiments are done, and to get some feeling for the size of things. I emphasized a few things from this general perspective. One of that was this perturbative scheme for understanding electrodynamic response, right? So I wrote down, one of the things I wrote down was this perturbative expression for, let's say, the polarization driven by an electric field, and we have a linear order, quadratic order, higher orders, et cetera. And so I'm going to talk about those higher orders in the latter half of today's lecture, but I was talking about linear response theory for most of it. We can, again, learn a lot from general considerations, and some of those general considerations was that symmetry is important. And so that's something I'm going to talk about today when I talk about various techniques. It's important to understand the symmetry of the system because that constrains the response function in various ways. We can use that to understand exactly what we're measuring, but also we can use it to do efficient experiments where we don't kind of, measure redundant information. Okay. The other thing that I had emphasized was we have these response functions in the linear response, but it's important to recognize they're complex response functions, right? They have real and imaginary parts. They're not separate things. They kind of are characteristic of one global response function that is going to be useful for characterizing systems. And for some systems, for instance, we want to know the imaginary part. That carries more information than we might have considered otherwise. We're going to have, for instance, in superconductors, the imaginary part of the complex conductivity is the thing that we actually care the most about. I talked about, from those considerations, Kramers-Kronig transformations, which is, if you will, the bread and butter of what we do in optical spectroscopies. Very often we'll measure one of the components of the complex response, but we need to know both. We want to know the complex conductivity, and so we'll use these Kramers-Kronig transformations. If we know, for instance, all frequencies, or at least a lot of frequencies, a broad range, we can use that to find the other response at any frequency. What comes out of Kramers-Kronig, one of the things that comes out of Kramers-Kronig is sum rules, right? And so we use sum rules, again, all of the time in optics to understand things in a reasonably model-independent fashion. We often start with trying to understand our data, even if we're talking about, quote, quantum materials. We start with classical models to kind of, if you will, hang our data on, because we find out, in fact, that some of the simple quantum theories give us exactly the same result often, or close to that result from the classical perspective. And so that turns out to be a very convenient and constructive way of thinking about things. So if there are no questions about any of that, kind of the preamble, the recap, then I'll just kind of get into it. Okay, very good. Okay, so again, large frequency range for solids. And one of the techniques that I want to emphasize, and I could spend weeks talking about all the different kinds of experiments can be done, and so this is kind of a very, again, idiosyncratic and opinionated take on what there are things that I've worked on and find interesting. So we're just running through them. One of the kind of classic techniques for looking at the electrodynamic response of what I would call small frequencies, tens of gigahertz, which is solidly in the microwave frequency range. Recall yesterday I said we should know about something about units. We're going to talk about gigahertz. We're going to talk about millieV. We're going to talk about inverse. We're going to talk about wave numbers. Tens of gigahertz, right? So what was the correspondence I gave you yesterday? You can remember 200 gigahertz is approximately 1 millieV is approximately 10 degrees Kelvin. So 200 gigahertz is, this is a resonator here, and resonators like this are something, you know, order typically about 20 gigahertz. So we're talking about things which are fractions of a millielectron volt. When we do microwave cavity resonator spectroscopies, what we're going to do is we're going to have a small, typically copper superconducting box. It's a cylinder. I should have had a picture here, not a schematic. About a centimeter or so across would be typical. Okay. You send microwaves in through one little hole. They, if you will, the microwaves come in, this box has a certain resonance frequency. You set up standing waves inside this box. And if the standing waves are set up, the microwaves can come out through the other hole. So you measure essentially the transmission through into this box and come out, and you might sweep the frequency and get a resonance, okay? And so it's characterized by two quantities, a center frequency, and then also a width. And then you go in and you put a small sample into this box. Again, for this thing, a few centimeters or so across, the sample could be fractions of a millimeter there, and the resonance frequency shifts and it broadens. We want to know the complex response. So we need to measure two things, and we measure two things. We measure the frequency shift and we measure the broadening. This is a little bit of kind of interesting history. The formalism for, it's kind of a clever idea. This frequency shift can be related directly to a quantity which characterizes what we call the complex, the surface impedance of a system. And that relation that relates the complex frequency shift to the complex surface impedance was first worked out by Schwinger in 1943 when he was not at the Manhattan Project, but working at the MIT Radiation Lab. So the original references are all from Schwinger working on radar work in World War II. With a technique like this, you can do very, very sensitive experiments to measure things like what Steve had referred to the other day or the day before. For instance, things like penetration depth can be characterized in different ways. This is cavity perturbation of a niobium sample, so a kind of conventional superconductor. This is the plot of the real part of the conductivity here, which shows this particular functional form as a function of temperature. This is the imaginary part of the conductivity. The imaginary part of the conductivity is proportional to the superfluid density or the phase stiffness, the helicity modulus, depending upon what particular language you'd like to talk about. This guy here, that little blip, that peak, this is a microwave version of the famous Hable-Schlichter peak. Hable-Schlichter peak is was a resonance of enhanced absorption that was found in nuclear magnetic resonance, which was really the kind of definitive first evidence for the BCS wave function, right? So when BCNS had come and basically come up with their wave function around that time, Charlie Schlichter at the University of Illinois had found that when he did nuclear magnetic resonance, a very similar thing, that there was a peak in the dissipation that was found just below TC before eventually it comes down. And this was unintuitive, right? Superconductors are superconductors. Why should they show more? An intuitive thing is that they should show less dissipation as you go below TC. But it shows more, and this was kind of non-trivial evidence for the BCS wave function. Yeah.
Where does the niobium sit?
Niobium is the little, there are different ways to do it. So you could do an experiment where you just replace the whole end plate or end plate here with a piece of niobium, but in cavity perturbation, it's that thing. So you imagine doing an experiment on an empty cavity, and then you place the little sample inside, positioned in some particular fashion.
So the cavity is coupled to the little bit of niobium there.
The cavity is this box that has the standing wave set up. And then if you will, when you introduce the sample, the frequency, the resonance frequency is somehow a function of the volume. But now, if it's a superconductor, you've excluded volume. So the resonance frequency goes up, right? The cavity is smaller effectively than it was, so its frequency is higher. And in fact, that's what you're actually measuring in this experiment is you're measuring the penetration depth, which is quite remarkable. The electromagnetic fields penetrate a little bit farther into the sample as the penetration depth, let's say, increases when you warm it. And the cavity is, the effective cavity volume is larger, and so the frequency goes down in that case. Yeah. And then there's a dissipative part. Okay? Yep.
By some kind of geometry size and kind of cavity.
Yeah. Yep.
So, but then now things are getting smaller and so on, and then I just always am wondering, as a experimentalist, will you worry about that some frequency you're using, you're using like let's say very very tiny cavity, and then your resonance
It's cavity perturbation in all cases, right? So you're kind of, you're working at a limit where, say, delta F over F, the frequency shift over the frequency is a small quantity.
Yesterday you showed us like gigahertz, range of
You mean the system meaning, like, for instance, the piece of niobium?
like very low energy, some rare earth magnet has a very small energy scale in the strict electrical energy scale.
What I'm characterizing then is the complex conductivity at the single frequency that I'm resonating at. And so it's useful for things like superconductors. Magnets it may be less useful for. We've done work with this on magnets, but superconductors have very simple optical response at low frequencies. There's a delta function, but if we're well below the gap, there's a delta function, and then there's a 1 over omega dependence in the imaginary part. And so, if I measure any frequency there, I know it goes like 1 over omega, and I'm looking for the coefficient of 1 over omega because that gives me the stiffness. What's that? Say it again. Yeah, I have that information. Yeah, I know it's a superconductor, for instance. Yeah. Yep, in the back first. Yeah. Yeah, I'm sorry. So what you actually measure is a complex susceptibility of the sample. And so I'm sorry. I actually took this from an old slide, which I was actually measuring a magnetic material. So if it's a Lewisly material with electric degrees of freedom, then you're measuring a complex conductivity. If it could be a material which has magnetic degrees of freedom, then you're measuring a kind of a generalized magnetic susceptibility. Of course, it's kind of both, and then it's kind of some in between thing. And I actually took this slide from something else. So for my example I give here, I should say measuring a complex sigma or epsilon. Yeah. My apologies. Yeah.
Can you get that you're showing that the peak is broad as well?
Yeah.
Maybe the shape changing other ways. Can you also clean it from that? It's not just the shift in the peak, but like shape in the.
Yeah, in principle you could, but that is typically a sign of something going wrong with your experiment. Yeah, in the sense that you're kind of overcoupling to the. In order for this formalism to work out, you really need to be in the limit of infinitesimal coupling. So you need these shifts to be tiny, and if you start to get weird asymmetries, Lorentzians in the frequency domain correspond to exponentials in the time domain, and so if you have non-Lorentzian line shapes, that means that you kind of have multiple ways that radiation is dissipating in the cavity because there's, it's presumably it's a superposition of exponentials in the time domain, and then that's not a good thing to have.
So just to be sure, what's inside the box is a cavity that's a vacuum, and then also a piece of niobium.
Yeah. So first it's nothing in there. It's just empty box, and then I take the cavity apart. I mean, we do it a little bit more sophisticated, but you could imagine this, and then you place this sample inside and put the box back together and measure again.
Then I need to solve some electrodynamics problem about what would the response of this cavity with a bit of niobium, with a bit of something inside it, with a different dielectric constant. Be.
Yeah. So that's the perturbation scheme from Schwinger, where you don't need to do the whole business. Otherwise, it would indeed be hard. You have some complicated set of electromagnetic fields, and you don't need to do that. There's a calibration between the frequency shift and the complex impedance. And that calibration needs to be done in some fashion, but one can do that. So there's a proportionality between the frequency shift and this complex impedance, which is the square root of, there's a bunch of factors in there, but it's actually the square root of omega over sigma. And so there's a proportionality between the complex frequency and the complex impedance, and that's called the resonator constant, and you can calibrate that in some fashion. It's also a complex number.
So actually, using this method, can you really measure the absolute value of the superfluid stiffness, or do you measure changes as a function of temperature in the superfluid stiffness?
It depends on the details of what you're doing. If you have a single crystal material, then you're generally measuring changes. If I have a thin film inside the cavity, then I can measure absolute values.
Yeah. Are you going to explain how that?
I wasn't planning on doing it. Yeah, I mean, I have gobs more slides. So, but I can talk about this slide for a long time. But anyway, there's another question here. Yeah.
The shift doesn't depend on the geometry of the matter, only on the volume, in the perturbation.
It does depend on its shape. That's right. So there would be it's classical electrodynamics, and so you would imagine there's a kind of a depolarization factor inside. Some approximations typically have to be made for, so the simplest, indeed, the thing that you could solve basically exactly would be an infinitesimally small ellipsoid placed in a region of extrema, of field extrema inside the cavity. And we're never in a limit where we have, but some people like to use needles or they like to use discs because we can approximate those as ellipsoids. Yeah. Okay, good. So this was a chunk of niobium though, and so we can, the way this can be done, let me say that Deepanjan asked, can we measure shifts or other calibrations can be done to get out the, so I can work with, I can make, if I know a piece of, I can take a piece of copper, which I know everything about its electrodynamics, and I can make it exactly the same shape as the superconductor and place it at exactly the same point, and then I can calibrate all the details from it. The most experiments that are done, the most sensitive experiments that are done are ones that I can measure shifts. So, so for instance, like famous experiments were done on the superfluid temperature dependence of the superfluid density on D-wave superconductors. These were famously done by people at University of British Columbia. And so there, they didn't care about the overall, they didn't so much care about the overall magnitude of the superfluid density. They wanted to see how the superfluid density was degraded because you have nodes, presumably, in a D-wave superconductor as you warm up. And so there, they cared about the temperature. They didn't even care about the magnitude of anything. They just wanted to know what was the power law. And was it, or was it not power law at all? Was it exponential? Was it S wave? Was it what have you? And so there you don't even care about what the actual vertical scale is. You're just caring about, fitting this here, and this is the Mattis-Bardeen form, which if they went to lower temperatures, you would resolve that it's exponential because it's niobium. Yeah. Okay, good. Great. Yeah, please. Louder, please. No, it's not. Yeah, it's it is so if I solve the Mattis-Bardeen equations for a S-wave superconductor, I get as the gap opens up, I get a gap-like feature in the imaginary part of the, in the real part of the conductivity that's getting larger and larger, and then I get a very non-trivial kind of absorptive feature at low frequencies that gains intensity as I basically make thermally excited Vogel U-bonds, and then I freeze them out. And it's not it's not an exponential at all. It has a very funny functional form, but it goes up and, it kind of gathers strength and then loses strength. And as it does that, and I'm following at one frequency, at a frequency in the gap, I get that maximum. And this is, again, the fact that there's a peak here is really sensitive to the BCS coherence factors. Okay. Yeah. That's right. And so it depends on basically how does the probe it depends on the probe. Different perturbations can give you different. There's so-called type 1 and type 2 coherence factors, and ultrasound attenuation goes down. And so this was also understood around the same time. I don't know the history of this very well, but I presume those experiments were done afterwards, and that was kind of an interesting confirmation of what had already been understood by Bardeen, Cooper, and Schrieffer, and then confirmed in Schlichter's experiments. Just because I'm rambling here, the famous 41 millieV peak of neutron scattering in the cuprates presumably is a momentum resolved version of the Abel-Schlichter peak that has to do with the coherence factors, but in a D-wave superconductor that's found at finite momentum. Okay, good. So a technique that we've used a lot in my group, and it's kind of been the workhorse for many things that we've done, is called time-domain terahertz spectroscopy. I like terahertz part of the electromagnetic spectrum to probe many of the materials that we're discussing in this meeting here. So going back to those temperature frequency units, right? 200 gigahertz corresponds to 10 degrees of Kelvin. So if we're talking about hundreds of gigahertz, tens of Kelvin is, tens of Kelvin is kind of a typical energy scale for many phenomena we're interested in. So hundreds of gigahertz. Terahertz spectroscopy was traditionally a difficult part of the electromagnetic spectrum to take to do characterized materials in. It's not because we don't have enough terahertz radiation. The problem is where we have too much terahertz radiation, right? Right now we are awash in the bath of black body radiation, which is coming from the thermal radiation around us. Kind of a conventional detector for infrared radiation measures the power which is incident on it, right? So I can have some detector, I can have a source, I have light that leaves the source, falls on the small sample, and is then falling on this detector, and there's some more additional amount of light falling on that detector, but that detector is getting clobbered by the bath of black body radiation that it's living in. So this is a much better way of doing it. And again, I don't want to get into all the details of it, I'm just giving you a kind of a rough idea, but we use an ultra-fast laser, which goes through a beam splitter. You get these two separate paths of the laser that go around here. We have an emitter, which is a variety of different ways of doing it, but in this setup here is a device which is called an Austin switch or a Hertzian dipole, and what it essentially is some electrodes grown on the surface of a piece of gallium arsenide grown in a particular fashion, semiconductor. This structure is biased by about 20 volts, and the gap in here is a few microns. And even though it's so small, the resistance of this is really large. It's a few hundred mega ohms. So the structure is biased by 20 volts across a few hundred mega ohms, and nothing happens. But then you come in with a laser, right, and you zap this thing, and you make the shower of electron hole pairs, and the resistance drops from a few hundred mega ohms to a few hundred ohms, and it's biased by 20 volts, and charge races across this gap and kind of jiggles on the scale of the electron hole recombination time, which is a picosecond. And so it's that acceleration of charge on picosecond timescales, which gives you this then emitted free space pulse right there, which then propagates around a table. We put a sample in the focus right there, and then it falls on a receiver where the detection is kind of the inverse of the generation. The difference is that in the detection, you have the emitter side is DC biased, and this is kind of biased, if you will, by the transient pulse, which is flying through space. It is a time-domain terahertz experiment. So if you will, we put a sample here. We could imagine that something is absorbed, so this peak amplitude is reduced as it goes through, but it could also be shifted in time. So that's measuring two things. We want to know the complex response. So reduction of amplitude, shifting in time, we can work out what the complex response function of the material is, and that's a feature of its spectrum right there. So you see peaked in this kind of terahertz, sub-tera, hundreds of gigahertz range, which is quite useful for us for the kinds of things that we want to look at. Yeah.
Sorry, where's the sample?
Sample would be right here. Yeah, so it's not in this schematic here. This is a bird's eye view of an actual experiment.
No, I'm sorry, I might have completely missed the point, but what does the emitter do again?
The emitter makes, so this is a laser, so it's 800 nanometer laser, it's 1.5 EV photons, totally misses the energy scale that we're interested in. It zaps this emitter, and it is focused on this, and that emitter is a semiconductor which has high resistance. The laser comes in and makes the shower of electron hole pairs, and the resistance of the switch drops, and charge kind of it's already biased, and it kind of, basically you're discharging a capacitor. It's a biased capacitor that then you're discharging, and as it discharges, it makes a pulse of radiation about a picosecond long. Inverse of a picosecond is a terahertz. Yeah.
Just
Okay.
out of curiosity,
Yeah.
does that mean you can just start operating in like millimeter or microwave frequencies just by playing around with that switch?
To some extent, you can tune it, yeah, but you can't, it's hard to go much higher in frequency because you start to run in the phonons of gallium arsenide or phonons of other things. Lower frequencies turn out to be harder as well because the laser has a finite wavelength. So if you made very, very short pulses, yeah, you can push that to as higher frequencies. To go to even lower frequencies, other aspects basically of how charge trapping works in these systems, how the particle current decays, these all kind of come in. So there's some tunability, but not much.
The difficulty is making the terahertz pulse in the first place. Like,
Yeah, and the detection.
right, so I guess I'm gonna ask, the problem of being awash in terahertz stuff at the receiver,
Yeah.
that's all?
That's solved because those are all incoherent photons, right? So they're kind of, your receiver is sitting at room temperature and getting bombarded by incoherent thermal photons, and they're all hitting with random phases, and they don't give you a current. Yeah, so I kind of glossed over the issues, but the way this works is basically you have these pulses that are coming. Yeah, if there's questions, I'm happy to talk about the details. The pulses are coming and kind of hitting this thing, and they're coming at 80 megahertz. And you've worked this out so that the second pulse is basically, let's say, sampling right here at one particular place. You're measuring the electric field here. And then you advance the delay stage, and then you sample at a different time. So you have the pulse is really coming at you're getting current microscopically is coming at 80 megahertz. But you don't have detection electronics fast enough to see that. So you kind of see this kind of net, you're kind of boosting current through the switch, particularly, at some time. And then you advance the relative delay, and you hit it somewhere else. You get larger average current coming in this fashion. And then by kind of sweeping out the relative delay, you can work this out. Yep. Yep.
And like how, for the detection part, how high does the terahertz power that you're measuring need to?
So in this experiment, it's small. We're very sensitive, and the powers are small. Yeah, we don't talk in those language too much. My student Will, who's here, might have some thought about that. But what we usually will talk about is in the electric fields involved. And so those pulses in this experiment here, well, you can read it. That's actually pretty good for an experiment like that. That's kilovolts per centimeter. But more typical would be tens of volts per centimeter. The experiments that I'm going to talk about in terms of nonlinear optics, then we need much bigger fields to induce nonlinear responses. And those are going to be hundreds of kilovolts per centimeter or up to a megavolt per centimeter. Yeah.
I mean, I only ask in the old electron hydrodynamics literature, there's this Diakonoff-Scher instability, which should be a terahertz source from a hydrodynamic.
I see. Yeah, I don't know anything about that. Yeah.
A problem is detection. It's like picowatt scale terahertz.
Yep.
Maybe why is the split laser set receiver also?
Because it is another detector. It's another switch which looks like that. There's an emitter and a receiver. And so if you will, the terahertz is propagating through free space. It's incident on this thing and kind of biases it, but nothing happens because its resistance is 100 mega ohm or a few hundred mega ohms. But then the laser comes in and zaps it, and the resistance of the switch drops, and it's biased by this transient field which is propagating through space. And so current can flow. So if you don't hit it with the laser, then the resistance will be a few hundred mega ohms, which is a lot, and nothing's going to happen. It's really stroboscopic detection. I mean, people are familiar with the notion of the stroboscope, this flashing light, and you can, see a rotating wheel goes one way or the other. And if the stroboscope is flashing at the right rate, you can basically freeze, the spokes of the wheel in place, and that's how you can. It works in it's a very similar fashion here. The pulses are coming at 80 megahertz, which is way too fast to detect. Yeah. So I'll talk about that. So we'll do lithium niobate, various nonlinear optical ways of generating the terahertz. The advantage of this is higher signal to noise, higher sensitivity in many ways, a kind of more obvious way of doing polarization resolve. The lasers involved are much simpler. They could be oscillators. Lithium niobate typically requires amplified lasers, which have their own headaches with kind of keeping going. And we need to use those for the nonlinear experiments, but if we'd like to use simpler lasers if possible. One thing I would say is that when I started doing this stuff, which was almost 20 years ago, I realized there was opportunity here. This world of terahertz had kind of been developed by people in kind of from a laser optics background. That wasn't my background at all, but it took a long time to get things going. We had to build everything in the very beginning. And as the years went by, you could buy more and more commercial parts of the system, and I would buy some of these things to try them out. I always liked what we did better. That's kind of changed in recent years. I mean, if you're an aspiring theorist who wants to just cut out the experimental middleman altogether, you can, for $130,000, buy a terahertz system and bring it into your office and set it up on your desk, and in 2 minutes be doing better terahertz spectroscopy than we did 5 years ago. Yeah. Okay, good. Okay, good. So I'm on my third slide, and I'm a half hour in. But that's totally good. That's great. We'll just go as much time as we have. So I want to talk about kind of some fancier things, of course, but let me give you one example of some, kind of a beautiful spectrum that is this is on bismuth selenide, so bismuth selenide topological insulator, but it's in a regime which is kind of highly doped, so that the topological properties of bismuth selenide topological insulator are not apparent. This is a plot of the conductance. So it's not the conductivity, it's the two-dimensional conductance as a function of frequency in the terahertz range. And as I mentioned, we got the real parts and the imaginary parts here. Those are the colored lines, and the dashes are some fits to the Drude model, which I spent some time talking about the other day. And then this big peak here, which is at 1.9 terahertz in the dissipative response. A lot is known about the phonons in bismuth selenide. Before it was a topological insulator, it was a thermoelectric material, right? So in the old thermoelectric literature, this is called the alpha mode. And so it's found at 1.9 terahertz. And it just gives you, again, a kind of a feeling, if I want to teach students about optical conductivity experiments, this is a good slide to show, because it shows the Drude response, okay, of the surface states, as it turns out, at low frequencies. And then this phonon that's here. And then you can kind of see this kind of dispersive behavior. That's what the imaginary part of the Drude response looks like until the phonon's dispersive behavior takes over. Okay. All right, so let's look at just some other things that we can do with time domain terahertz, and then I'm going to start making references to some of the things that we talked about yesterday. I did show you this slide previously, so many of us are interested in this idea of the linear T resistivity in the cuprates, sometimes called Planckian resistivity, and the idea again is that this is old data, 1987, probably before most of you were born. The resistivity is a function of temperature, okay? This lanthanum strontium copper oxide has a transition temperature way down here. That's that little fall off, right, at 30 or 40 Kelvin. And it basically is linear in temperature all the way up to the melting temperature of the crystal, which is some 1200 degrees, right? So that's this thing. What does it look like there? It is red hot at that, so it's a, really remarkable behavior. Linear in temperature over this whole range here until this thing is glowing like it's a hot ember. This is the conductivity as a function of frequency, okay? So this is the resistance here, and so these values here could come from taking the zero frequency, the inverse of the zero frequency part of this signal. Now, one of the things that we've discussed in terms of the Drude response, the resistivity is a scattering rate times the mass divided by a density. You don't really know what's going on with the mass in this system. You don't really know what's going on in the density of the system. But the scattering rate in these models we discussed is just the width of this feature. And it is related, and I'll talk more about this, momentum relaxation rate as a function of the temperature. And so here, it's almost basically, again, in a completely model-independent fashion. The conductivity, we use the language of not, quasi-free electrons, masses, densities, but this is all more general than that. The conductivity, this frequency structure in the conductivity is the relaxation, it's the width here, is the relaxation rate of the current, right? I mean, that's just the definition. So it's kind of, we might use the language of non-interacting electrons, but this width of this thing, and I have to emphasize this to referees all the time, that they'll say, oh, you measured the width of this feature, but you don't know it's a non-Fermi liquid, blah, blah, blah. It has a physical significance. It's the rate that current relaxes in the system. If I have a current that's flowing and I kind of take the electric field off, the current will eventually stop flowing. That's the width of this feature here, right? And so it shows this remarkable momentum relaxation rate as a function of temperature, which has this form, which is essentially kT divided by Planck's constant times a small number, which is of order 1. Okay, and so this is measured nicely with these time domain terahertz spectroscopy. Those are temperatures. Yeah.
It's like by the red, how do you extract the?
Yeah, so exactly, that's a good question. So this is a very flat curve here, so you can't get out of width very well, but we're measuring, I didn't show it, this is the real part, there's imaginary part, and so that would be a slope here of finite with a line that's going up like that. And the ratio of these, I mean, what we do is we fit it, but you can see it in the raw data. If I looked at the ratio of these quantities, that's omega times tau, right? So it just kind of comes right out at, again, a kind of very, very simple level. And you can see this here is hard to get any detailed information about its width. But if you looked at the
If you take that tau and then you fit, let's say, the red curve to a Drude peak.
Yeah, it'll be with a half width out here or something like that. Yeah.
But it's not a bad fit.
It is not a bad fit. Yeah, so it's not obvious in this data, but if I measured out the higher frequencies, you would see that it's, when you start getting out to higher frequencies, then you'll start to see that there are deviations from the Drude form, and I'll talk about that in a moment. So, but at low frequencies where temperature is much bigger than the frequencies involved, the Drude form in the cuprates works quite well. Yeah.
Not sure if you're going to talk about it, but this is the overdose. Is this where you have the uncondensed carriers, or this is the different.
This is not so overdoped, but yeah, so you mean, yeah, when you go into the superconducting state, then you start to see very little changes. When you go to the superconducting state, you get these indeed uncondensed carriers. So you're talking about them?
Traces I'm seeing here.
These traces here are slightly actually in the superconducting state because you see the spectral weight kind of comes up and then it comes down a little bit. But this is not so overdoped. We start to get very anomalous behavior when TCs start to be about 15 Kelvin or so. So you're not quite there yet. You're seeing some little bit of hints of it there, but it's not the major features of the data. Yeah. Yeah.
More fun with the plot on the right, but the one on the left, don't we expect linear increase in resistivity for high temperatures anyway?
Okay, so right, so that's a good question, and actually, if I get to it, I'll talk about our recent experiments using nonlinear optics where we address this issue. But the question was, don't you expect linear T resistivity in a metal? And you do at temperatures well above the Debye temperature or the Bloch-Gruneisen temperature. What is difficult to understand, you can certainly come up with various temperature regions which will give you linear T resistivity. What's difficult to understand is how you could kind of come up with one mechanism which will, if you will, pass the baton from 40 Kelvin all the way up for 1200 Kelvin without kind of changing the slope. Right? That's something which is harder to understand how you might get that, right? We also need to get very, very low Bloch-Gruneisen temperature. And people have argued that you can get this with phonons. I think the recent data that I'll talk about, also what Will's working on, my student Will, who's here, I think shows that this picture of phonons doesn't work. Yeah. Yeah, go ahead, Dimitri. A question. Signs for phonons are down. Okay, yeah, thumb down for phonons. Good. Yeah.
I guess almost an identical question. Are you able to do these fits above the MIR limit? Like, does your
yeah, not so this goes. So this data here goes up to 100 Kelvin.
But
yeah.
Your MIR limit across the.
Yeah, so you would not find anything particularly if this is all you had. You wouldn't find any. You wouldn't say that there's anything that particularly anomalous about it. I mean, it is at very low. It's at low frequencies, but I probably can cook up some mechanism where I could get linear and T resistivity from 30 Kelvin to 100 Kelvin without. But I know that this sample shows resistivity that's linear to even higher temperatures. I can't measure it because then things get very, very flat, as Andy was kind of implying. But based on what I know about the totality of the Coop rates, I'm confident that I'm in a regime of linear and T.
What is the device?
Yeah, so it depends on definitions, right? It's a Debye model is a rather approximate thing, but if you would fit it to heat capacity in the Coop rates, it's something of order 150 or 200 Kelvin.
Because if it was well above, say, that range, you'd expect like little Ds, right? As you reach each additional.
That's right. Yeah. Mm-hmm. I don't think so. Yeah. So we've done some work with this, and so one of the nice things about some terahertz spectroscopy like this is that we can get this rate without, almost making no model assumptions, right? So there have been papers where they measure resistivity and then extract out the density through Hall effect, which we can believe or not believe, but it's certainly a very model-dependent thing, and then try to get gamma out, as well as putting in some value for the mass, right? So make a bunch of assumptions, assume that you can measure the density accurately through a Hall effect, which you probably can't, and to get out gamma. And lo and behold, people get out the numbers which are almost exactly 1. So we don't have to do that. And for this particular data that I showed you, it actually turns out to be 1, but there seems to be a doping dependence to it. And so there's a recent paper we have which talks about this. Yeah. Okay, good. That's slide 4. I'm 45 minutes in. Very good. I'm happy about that. I like the fact there's lots of interest. Let me talk a little bit about, come back to one of the points that I made yesterday. So I talked about Kramers-Kronig and I talked about some rules. I wrote down this form for the optical conductivity, right, which is our Drude expression. I'll put this here. Let me put it as 1 minus I omega tau, right? So that's the Drude expression. And one of the things that I had mentioned yesterday was that I wanted to think about this mass here as a quantity which has a frequency or energy dependence. Right? That comes out because I can imagine there are different energies. I know that if I take this quantity, as I discussed in some rules, if I integrate it to infinity, and I know the number of electrons are there, the mass that I would extract has to be the free electron mass, right? I can turn the problem around the other way and put the free electron mass in and kind of ask, like, what's the effective electron density as a function of energy? And that was this plot I showed you yesterday of this beautiful plot with all these kind of thresholds that you saw in aluminum, right? But what we can ask is, if we know the density of electrons and mass, we can get out a frequency-dependent mass. The other thing that we can do is we can put a frequency dependence on the scattering rate. And in fact, we have to do that if we are changing this mass in some fashion, because we have a Kramers-Kronig pair of sigma 1 and sigma 2. And if I go and I change the mass and make it frequency dependent, that's going to give me one of the complex components. Essentially, it's going to be proportional to the complex resistivity. And then I'm going to have to also introduce a frequency dependence to tau. So I can go through and solve this model, this expression for mass, or I can solve it for tau or 1 over tau, and then I got a frequency dependent scattering rate, right, which is like a self energy, and a frequency, like an imaginary part of a self energy, and then I can solve it for the mass, which is something related to a real part of the self energy, those kind of optical self energies, if you will. Okay, good. So that is relevant to what I talked about yesterday. So there's this interesting material here, cerium cobalt-indium 5. Okay, so it has the distinction of being the highest temperature heavy fermion system. So you take the system, you cool it down to low temperatures. At high temperatures, it has these conduction electrons and this kind of localized spins. You cool it down to low temperatures. There's a hybridization, and you get a regime, heavy fermions. There's a hybridization of the conduction electrons with these spins, and you get with the local moments, and you get enhanced masses, when this system can, depending upon estimates, can be large as about 100 free electron masses, right? Some materials in this material class, I don't think we have too many talks about heavy fermions in this meeting, but there are materials where this enhanced masses can be as large as 1,000 free electron masses, which is really remarkable, right? Electrons almost with the effective mass of a proton. Okay, resistivity of cerium cobalt-indium 5 has this particular form here. It is starting from high temperatures, that's 300 Kelvin. It kind of comes down, that's like a normal metal. And then you get this increase, and this is where you start to get incoherent scattering of the electrons off the local moments. And then there's a peak, and that's when you start, it kind of transforms into some kind of coherent scattering. This is, where is that peak? Something of order 30 or 40 Kelvin. And then it comes down to low temperatures. And what was pointed out, this was in, it's actually Jean-Pierre Paglioni's PhD thesis. This is a plot of resistivity as a function of temperature, but now at a few different fields. And one of the things that was noted was that if you go out to really large fields, you get T-squared resistivity, but there's a large region in here, which was referred to as the non-Fermi liquid regime, basically because you have linear in T resistivity over a large range. It is not linear in T resistivity over up to 1,000 Kelvin. It's linear in T resistivity over a very small frequency range, but they want to think about this scale down in here as going linear in T. Okay, good. So now remember again, when you measure resistivity, you can have, very often when we're thinking about the temperature dependence of the resistivity, mass doesn't change, but we're thinking about the temperature dependence of the scattering rate, right? But there's no assumption that you can make in a system like this, and perhaps it's not a very good starting point to think about the transport coming from the perspective of a temperature-independent mass, because we know from things like heat capacity that the mass changes dramatically. And so this is plots of the real and imaginary conductivities, right, as a function of frequency at different temperatures, starting here at 150 Kelvin. At 150 Kelvin, there's some little blip that's happening at the lowest frequencies, but then it's essentially just completely flat. Here is a small upturn, and this is kind of maybe relevant to what Andy was asking about earlier. If I ignore that little upturn at the lowest frequencies here, it's essentially just completely flat. But here I can resolve that slope, and the ratio of those quantities gives me omega times tau. This is another version of it here. This is at 80 Kelvin, and real and imaginary conductivities, 20 Kelvin, and you start to see that you get this structure. These dashed lines are not fits to the Drude model. That's in fact not fittable just with a single Drude, but we can look at this lowest frequency regime here and realize that it's approximately Lorentzian, and that there is a large component of the current which has time correlations which relax exponentially in time. Exponential in time is hence Lorentzian. Yeah.
So this is I thought that the imaginary part of conductivity should be odd. So why do I see the blue and purple curve like not going to zero?
Because it doesn't go to the lowest. It doesn't go to the lowest frequencies. Yeah, it'll come up and then it'll go down. Yeah, and then indeed beyond. Yeah. Yeah, it's not plotted to 0. Yeah. Okay, good. So then another thing that we can look here is this is a plot of this scattering rate as a function of frequency extracted in the fashion that I discussed here. The explicit expression is right there, right? So it's the real part of 1 over sigma with some prefactors in front. 1 over sigma, that's a complex resistivity. So it's the real part of the complex resistivity, gives me a frequency-dependent scattering rate. Again, we kind of have in mind some kind of weakly interacting quasi-particle picture where electrons are scattering. But what this really corresponds to physically is the rate that current is relaxing at that frequency. Okay. When I plot that as a function of frequency, this is what I get here. Okay, and I can plot it with this particular form here, a constant plus this piece here, which is a power law, just as a kind of a starting point to understand the data. And that's the power. It comes in at the lowest frequencies with something very, very close to 2, which is the canonical Fermi liquid form. But I had linear and T resistivity. So I have a frequency dependence, which goes like omega squared. And if it looks like a Fermi liquid, then I would expect that the resistivity is going T squared, but the mass is changing. So I can also, through this expression, look at the mass as a function of frequency and as a function of temperature, and that's plotted here. And so what you can get out from this, it starts out at some small value. And one way of doing this is to normalize to some effective band mass. And let me not talk about the details of that, but you see this as some kind of small number at high temperatures. And then it comes in and gets greatly enhanced at the lowest temperatures. And if I plot this scattering rate, there's a bunch of other things in this plot. That's the resistivity right there. That's the scattering rate as a function of temperature of this quantity, which is this kind of normalized scattering rate, and you can see it's T squared. So I think that this essentially, if you will, solves the problem of cerium cobalt 5. I don't think it's a non-Fermi liquid at all at these temperatures, right? So I think there is a and it basically comes out in a kind of model independent fashion. If it's a non-Fermi liquid, there's no reason to think it's a non-Fermi liquid from the transport, right? There's a strongly dependent mass. You can see it directly in the same measure as you see the scattering rate, and the scattering rate is omega squared and T squared. Yeah, so that's a good question, and I don't have the answer to you. Yeah, so there's Dmitry and Andrei Chubakov have some very nice papers where they point out that there should be a strong constraint on the relative coefficients of omega squared and T squared, and I don't remember actually how it comes out here, but I should know that. Yeah. Yeah.
Is there temperature dependent quantum
Uh,
oscillation?
There is, and I don't remember all the details of it, but I'm going to show some experiments that we're doing, not on this, we are doing on this, but I'll show the experiments that we're doing with high magnetic fields, look at cyclotron resonance. And so those experiments have already been done, and we're analyzing them now. So what we want to look at is the cyclotron resonance mass, and then the mass that comes out from, say, Shubin-Acosta-Haas oscillations. And those will be interesting to compare. Yeah. Yeah.
With a large magnetic field on.
I'll talk about that in a minute. Yeah, that's what I was just referring to. I'll talk about that in a minute. Yeah. Yes, presumably, presumably it will. But if you get to really low temperatures, then T squared becomes flat, and it's hard to see, right? So typically, we need a little bit of temperature to see dependences. I'm not sure that we know from an experimental perspective what the mass is doing, but presumably it does roll over. What does the heat capacity do? I don't remember, but I presume it rolls over. Yeah, the coefficient of the heat capacity, which is another measure of mass. Yeah. There are multiple Fermi surfaces. Yeah, so that's. Yeah, almost certainly that's the case. And again, but you can think of this, what I would put it like this is, do we think cerium cobalt 5 is a non-Fermi liquid? Is there evidence for that? And I would say no, there's no evidence for that, because you might have put credence into the fact that there was linear T resistivity, despite the fact there were multiple bands. But we can show that there is this scattering rate that, as I write here, it has physical significance because it's really the rate that current relaxes, right? Which is macroscopic quantity. Yeah. Yeah, I mean, roughly that's what's going on. That's right. Yeah. So there's, I mean, I wouldn't say that it's not, approximately that's true. Yeah. Yeah. The what? The single ion condo temperature, I don't remember, but the condo lattice temperature you can pull out from this peak, which is something of order, it's actually right there. So it's something of order 30 or 40 Kelvin. Yeah.
So maybe I can ask about refacing the story of DC system.
Uh-huh.
I know that doesn't rely on motion of vector mass.
Yeah.
for starting with.
Yeah.
Einstein relation.
Yeah.
Okay, so conductivity is compressibility times the diffusion constant.
Yeah.
So is it correct to say the diffusion constant is going like 1 over T squared and compressibility is linear in T?
Yeah, I think rough. So you want the diffusion goes 1 over T squared and the compressibility to,
Be proportional to
Yeah.
T so that the conductivity goes like 1 over T, which is a linear system.
it may be correct. Certainly some partition, I'm not sure that's how it all works out, but certainly. No, is there a way to measure the diffusion constant directly? I mean, we usually get it out from transport, right, from Einstein relations.
But then you have to know the compressibility.
Yeah. I mean, there are ways, for instance, to measure thermal diffusivity,
Sure.
right? Yeah, I don't know if there's ways to measure electrical conductivity in a direct fashion. Yeah. So okay, let me move on from this. So this gives you. I want to bring it back to what I kind of. The reason we can say all of these things is basically based on yesterday's lecture, right? Kramer's Kronig, the kind of utility of simple models, even when you don't think those simple models have direct applicability. The simple model is a useful way of kind of hanging your data on, and then you start to see deviations, right? So what is this frequency-dependent scattering rate? Here, where? Here, frequency-dependent scattering rate, it means that the form of this Drude response is not perfectly Lorentzian, right? So I might have fitted to a Drude, but there's a high frequency tail, and that's what I would focus on as something being interesting and notable, right? Is the deviations from Drude, right? So even if we think classical models are not useful for their, still, they're not applicable, they're useful starting points to think about deviations, right? So I think this is a kind of a useful way of thinking and understanding data. We start from the simplest thing first. Okay, good. So let me talk about then, I added, Sentinel made a comment earlier about axion electrodynamics, so I added a slide or two, but I also want to talk about magnetic fields. One thing that turns out to be very, very useful is when we start to bring extra information about measuring polarization rotations. So the Faraday rotation is the rotation of light transmitted through the sample. Right? Kerr rotation is the reflection of light that is reflected off the sample, right? So if you were some 19th century optical scientist and you just discover these simple things, you get to put your name on them, and we call them, right, Faraday. Well, Faraday discovered a lot, but Kerr discovered two things, and they're both called the Kerr effect. The simple schematic of how we would do an experiment, again, it's time domain terahertz. So we have this pulse, right, which is limited in time, about a picosecond, passes through a sample, has its profile changed in some fashion. And then there's different ways that we've done it over the years, but we have some polarizers that we put in and then detect out the polarization that comes out here. So there's been various different generations of this. And what we can do now, that actually slide is outdated. It says 10 millidegrees sensitivity. We've been able to reduce this now by maybe about a factor of 30 on a good day. So we're fractions of a millidegree. I talked about symmetries yesterday. And so if I gave you the simple example of a system which has a C4 symmetry, I can take it and turn it by 90 degrees. If you perform the same analysis for a system with C6 symmetry, as I'll give you the example in a moment, you get a Jones matrix. This is this transmission matrix that has this particular form here, right? That has equal diagonal components and it's anti-symmetric here. And so that's all very useful because we can do a very simple experiment to measure the Faraday rotation. And we learn basically everything from that about the Jones matrix. Okay.
Sorry, that's the second
one. Blue in this plot is representing, no, these blues are representing projections in the two directions. So I'm thinking about polarization resolving this. And so, yeah, you can't quite see it from this, maybe it's slight here, but this pulse is linearly polarized and it's passed through the sample and it's become rotated and you're getting this itty bitty projection this way and then a larger one in that direction.
This is a linear response.
We're thinking only about linear response here still. Yeah, exactly. Yeah. Okay, good. So we've applied this to a lot of different things. One of this is topological insulators. And so what I want to think, let me give you a brief interlude here, and that is about the notion of magnetoelectrics. And so yesterday I wrote down this perturbative form of, say, the polarization as a function of electric field. I mentioned briefly that we can think about adding other terms. Sometimes these are cross terms of E and B, but I can imagine adding a term where I get polarization when I apply a magnetic field, or I get magnetization when I apply an electric field, right? That's not the usual state of affairs. We usually get magnetization when we apply magnetic field, or polarization when we get an electric field, but I can get these cross terms. That's called a magnetoelectric. And it was first pointed out that there were certain magnetic point group symmetries of some crystals that allow this cross response. You have to break inversion to get there's some particular caveats that I can get into about topological insulators, where the details about symmetries and how they're important for quantizing response functions. But in the cold school magnetoelectrics, as pointed out by Jalashinsky, you have to break time reversal and inversion to get this response. That's this response is actually quantized, and again, there's other considerations when we think about either one of those quantities being a symmetry. A famous magnetoelectric is Cr2O3, we call chromium sesquioxide. It's this beautiful green color here. It's used as a pigment. That's what it looks like. It's a mineral as well, but again, it's a pigment. And this famous painting here, the train arriving from Normandy by Monet in 1877, the green blue color pigment in here, that's chromium sesquioxide. It's a magnetoelectric. If you apply an electric field to this painting, you'll get a magnetic field out. Don't try this at home. Yeah, or in the Musée d'Orsay. Okay. Topological insulators, there is a way that we conceive of them, right, as bulk insulators in the ideal, but with surface states. But if we want to understand them as, that's kind of an artificial model, if you will, right? It's all topological insulator. So if I want to write down a macroscopic homogeneous response function for the whole system, I can think of it as a magnetoelectric system. And so as Centil measured, I threw this slide in because it was measured earlier. We measured this in the context of doing these terahertz polarization experiments. What happens when you send polarized light and it passes through a film? You can measure the Faraday rotation, and it's quantized. If you measure the Faraday rotation and the Kerr rotation at the same time, which we can do, you can measure the fine structure constant. It's a purely all optical experiment, a terahertz measurement where you're sensitive to the fine structure constant. This is the analogous experiment to seeing quantum Hall plateaus for the topological insulators. So if topological insulators are materials like quantum Hall systems, but in 3 dimensions and with time reversal symmetry, you can ask, is there something we can measure that's quantized? And the answer is yes, we can think of them as magnetoelectrics with a quantized magnetoelectric coefficient. The ideal experiment would be to have a hunk of this thing and put it in a magnetic field or an electric field and measure this magnetoelectric coefficient, which would be the fine structure constant. That's challenging for various details that I can get into. It's much easier for us to measure this polarization rotation, and so that's what we did some years ago. Okay. We could apply magnetic field in time domain terahertz, the question was asked, and when you're doing that to a metal, the general idea is that you'll get cyclotron resonance effects. And so again, we can start with those classical equations of motion I discussed. We could add just the Lorentz force term here. We can think of the optical conductivity as I was writing something kind of very similar to this, but when I was writing this, I was thinking about the system, let's say without magnetic field, where I was thinking of it in XY coordinates, but I can think of it also as a response. This is a response of, say, current in the X direction to an electric field in the X direction. But I can also think of responses to right or left circularly polarized light. And that's, again, one of the advantages of the symmetry decomposition that I talked about, is that because we know the complex form of the symmetry properties, the complex form of the Jones matrix, we can measure in whatever basis we like and then transform into whatever basis we want. And so one basis we find very useful is you can't really measure this directly in terms of measuring the response to right and left circularly polarized radiation. But we can measure in X and Y, and then we can transform. And the Drude model is a particularly simple form there. It's 0 with no Lorentz force. It's just a Lorentzian centered around zero frequency. And when you put a field on it, it really is just that you displace the zero frequency pole to the cyclotron frequency, and you can just watch that. Okay. That's data there for the cuprate superconductors. So this was an experiment that we did in collaboration with a beautiful experiment that was developed at a beautiful apparatus that was developed at Los Alamos. This is the real and the imaginary parts of the conductivity of lanthanum, strontium, copper oxide for positive and negative frequencies. And here we're going to use that to represent right circular polarized light, like e to the I omega t, and left circular polarized light, e to the minus I omega t. Again, makes sense to plot these as positive and negative frequencies. And I did show this plot yesterday. That's zero field here, okay, peaked at zero. And then as you apply a magnetic field to it, we can fit the real and the imaginary parts at the same time. And there's this shift. And from this shift, that's the cyclotron frequency, it goes within semi-classical theory, EB over the mass. And so you can look at that shift of the cyclotron frequency as a function of magnetic field and pull out the cyclotron mass. And it has this very interesting dependence as a function of magnetic field, quite different than what I had implied yesterday with that plot of the mass got from inertial measurements as a function of the mass, something proportional to mass, from heat capacity. This is the mass in blue here as determined from heat capacity experiments. And this is the mass as captured from these cyclotron resonance experiments. And you can see that they just, they don't resemble each other at all. They're just, one has this kind of maximum and the other one is just changing in this fashion. And so it's very much counter to that plot I showed you yesterday, which was what I said, I wanted to take that as kind of evidence for the quasi-particle, the validity of the quasi-particle concept, whether that's what the takeaway message is here or not, I don't know, but this is something we're thinking a lot about. Again, I want to emphasize the importance of the experiments in this. This is time domain terahertz spectroscopy. We're only able to do this because we can measure these complex transmission coefficients. We measure two things at a time because we want to get two things, sigma 1 and sigma 2 at all these frequencies. We get a lot of information from measuring field dependence, the polarization dependence, and the frequency dependence. One of the things we've done with this is have long-term collaboration with people at Microsoft who are trying to characterize, this is for this effort to do quantum computation on nanowires. They're looking at strong spin orbit coupled semiconductors proximatized with a superconductor on top. It's hard for them to learn about the 2D electron gas buried below the superconductor, the superconducting layer, but we can look through that and see cyclotron resonance. And so, it has relevance, let's say, to interesting materials, but on the industrial side of things as well. Okay, let me just finish up with techniques. And kind of an old, so there was a lot about time domain terahertz. I showed a bunch of experiments from my group. Older way, but still powerful way of measuring the optical response is something called a Fourier transform infrared spectroscopy, typically called FTIR, right? So this is a kind of a classic way of measuring things. The frequency ranges that one measures here, let me show you maybe I'll go 2 slides down here. This is an example of a sample. This is on magnesium diboride, the highest TC conventional superconductor. We measure in a sample like this, in an experiment like this, the reflectivity as a function of frequency. And here you see these terrible units, right? Wave numbers. What's a wave number? Remember from my plot, 10 wave numbers is about 10 degrees Kelvin, which is about 1 millieV, which is about 200 gigahertz, right? So a wave number, that's an easy thing to remember. A wave number is about a degree, right? So this is something of order about 3 electron volts here. This is the reflectivity as a function of frequency. This edge, that's the plasma frequency, right? So that's a kind of characteristic shape for a metal. The reflectivity is very high, close to, in an ideal metal, would be close to 1. And then where the dielectric constant goes through 0, goes from being negative to positive, you get this steep drop. And then, something else happens at the higher frequency. So the way these experiments are done, excuse me, let me go back down there, is we might do an experiment on a sample. We have light coming in, reflecting off, but we don't distinguish the phase, okay? We would measure the light coming in, going off, bouncing off the sample, falling on a detector, which is typically like a bolometer or some system like that. It warms up a little bit when radiation hits it. And so that's a detection of the incoherent radiation coming off the sample. And then we would go, for instance, and we can come in with this little bit of gold and evaporate there and look at the ratio, and you can get the reflection coefficient. That's what you would get. You just get the absolute value squared of 1 minus the square root of the dielectric function. That's not doing a whole lot for me because I'm a physicist. I don't care about reflection. I want to know the complex response functions, and I only measure a single thing at each frequency. So what do? We talked about Kramers-Kronig, right? We've talked about Kramers-Kronig a lot. One of the things that's useful for me at low frequency was being able to understand and set these sum rules, but here it's an integral part of the experiment itself. This is the Kramers-Kronig relation. There's the reflection coefficient. Light is reflected from the sample if it's a perfect conductor, and it's reflected with unity reflection coefficient, but there's also a phase change. And if I know the reflectivity at all frequencies, I can get the phase at any frequency. Of course, I never get the reflectivity at all frequencies, but that's a lot of frequencies there, right? So that's from really low frequencies to really high frequencies, and I can come up with some kind of asymptotic form on the high frequency side and on the low frequency side. And that's how this was kind of conventionally done. We do a little bit of these experiments in my lab. It's kind of, it's very powerful. It's very useful. You can make images like this. This paper that this is from was called The Two Colors of MGB2. The superconductor looks different colors when you rotate it in different directions. But, it's at some level, I always felt kind of inelegant. If I care about the superconducting gap of MGB2, which is a scale of a few milli-electron volts, I got to measure out to 3 electron volts in order to know what's going on at the lowest energy scales. So we prefer to do time domain terahertz spectroscopy, which has everything right there. Okay, so that was my first 15 minutes. Lots of questions. I don't know if there are any questions on that, and I'm going to kind of shift. Otherwise, I'm going to shift gears to the nonlinear parts. But I don't know if there's anything on this. I'll kind of stop there for a moment and ask if there are any questions. That data is in the superconducting state. Yeah, it actually changes color when it goes superconducting. Slightly when it goes superconducting. The plasma frequencies shift a little bit, and it changes color when it goes superconducting. You have to use polarizers to see it, and it's subtle, but it happens. Yeah. Okay. Good. All right. Good. So let me bring up another. Okay. Good. Very good. So that was lecture 1. Again, linear optical response of quantum materials, introduction to linear response theory. That's one of the things I want you to take away from that is the general structure here. Somebody asked yesterday when I started presenting this memory function, isn't this just linear response theory? And the answer is yes, but it's a particular realization of it. But this kind of is a very powerful set of ideas that we can use to anytime we can write down these kind of memory functions, which lead to causal constraints, which lead to Kramers-Kronig, applies to all different kinds of things. There's applications of this in the recent world of correlated electron systems to ultrasound attenuation. Again, that's a response function which has causal constraints on it. Okay, but I call that the past, even though it's still quite a bit of our present. I want to center now on this idea here of nonlinear optics of quantum materials. I'm calling that the present, but I also think it's a fair amount of the future. So any dynamic-driven system can have nonlinearities, right? So frequently those nonlinearities are a source of complication, right? We like linear response for all the reasons I talked about. It's simple and it's powerful. We can say a lot of model-independent things, reasonably model-independent things from it. But nonlinearities are ubiquitous in any physical system. Often they're a source of complication, but they can also be a source of interesting phenomena, and they can be an important source of information. We should be careful about doing these experiments, or judicious, if you will, because I don't think complexity for complexity's sake in complex correlated systems is necessarily a good thing. But there are things that we can look at where we can get unique information from looking at the nonlinear response. Okay? So that's what I want to emphasize. As I mentioned the other day, we want to generally think about the electromagnetic response of a system in this kind of power series here, where that first term, that's the linear susceptibility, and there's all these other potential terms here, chi2, chi3, et cetera. Generally, chi2 is going to only be allowed in systems which break inversion symmetry. So, a classical cartoon of that is just this anharmonic potential well here, an asymmetric potential well. You can kind of realize that I can get these kinds of chi2 responses only from a system like this, which has broken inversion symmetry. They're different kind of processes, and this is going to be one of the importances of nonlinear optics, is if I have, a ground state and excited state, and I'm going to excite it, there's only basically one way typically to go from the ground state to excited state if I have just a two-level system. But if I'm thinking about the nonlinear response, and there are other levels in the system, there are many potential ways I can get to that particular excited state. And each one of those ways carries different information about the physical system that I can use to understand it in various ways. Right? They're different physical processes, and some of them, they go by various terms. This is an old subject, obviously. And there's a lot which is already known. I think what's happened in recent years, and I'll talk about this, is one, the notion that some of these nonlinearities are related to structures that we care about, things like Berry phase structures, and also the fact that now we can do nonlinear experiments not at 1.5 electron volts, as was typical in the field, but now we can do them in the terahertz range at a few millieV, and they become relevant. But these things have names based on the old literature, and they're Chi2 responses, and they go things like second harmonic generation. 2 photons come in, and 1 comes out with double the frequency. We can have a third harmonic generation, 1, 2, 3 up, and 1 comes down. Difference frequency generation, we're going to think about positive and negative frequencies, right? 1 frequency up, 1 down, and then maybe a third frequency which is emitting. These are both Chi2s. This is Chi3. This is a particular process which is going to be relevant for what we're going to mostly talk about, which is so-called 4-wave mixing experiments. So 2 frequencies up, 1 down, and then the 4th one out. I want to make a comment here. We need to have a slightly different notion of what we're measuring and what it means than we would in linear response. So typically with linear response experiments, it makes sense to use a language like, I had a source, I have a detector, I put a sample in between, the light was going from point A to point B, and it got absorbed in the middle, right? So that's an easy language to use. That language is not useful for us in nonlinear optics. What we want to think about is that we have a field. The field is driving a response in the sample. That charge is then, let's say, oscillating, and it becomes a new source of radiation, right? So that doesn't lend itself to this notion of absorption. I can use this idea of a secondary source of radiation for linear response. That's what happens in a metal, right? If I have radiation that's incident on a metal, and that metal is, we might say it's absorbing, but another way of saying it, it's driving a current, which is that current is now becoming, basically making that metal film an antenna. That antenna is broadcasting radiation, which interferes on the far side with 180 degrees on the far side. And I can call that absorption, but I can also call it interference on the far side of the film. But that's the idea, is we want to think about samples are going to be driven, and they're going to be new sources of radiation. As I mentioned, this is an old field. The discovery of optical nonlinearities was discovered, this is in 1961, within less than a year after the invention of the ruby laser. This is that first paper in PRL in 1961. You can read, so that is the primary signal here, which is basically 700 nanometers. So this is wavelength, and this is the intensity that they had found coming out. This was going into a piece of alpha quartz, I believe. And so you can read what it says. The arrow at 348 nanometers indicates a small but dense image produced by the second harmonic. And there's nothing there. There's a famous story. They actually thought this little speck was a dust on the photographic plate, and the copy editor took it out. So this major seminal paper enters and this huge field, which is now $1 billion industry, multi-billion-dollar industry, enters the physical literature with this kind of mistake scrub. And here we are for the present day. So that's a Chi2 response, right? So it was second harmonic generation. They used like 750 nanometers, and they got out something like 325 nanometer light, right? Produced at double the frequency. Chi2, what we now understand is that Chi2 nonlinear responses are sensitive to Berry curvature in a way that is very diagnostic of particular structures in Berry curvature. And so this has been done by a bunch of people, and I don't want to spend much time on it, but there's been various predictions for this. This is some data from Joel Orenstein and Joel Moore, actually done in Darius Torchinsky's group at Temple by Liang Wu, is a former student of mine who was a professor, was a postdoc with Joe at the time. And this structure here that they measure of this optical nonlinearity, which has this particular form, again, is very diagnostic to Berry phase structures in the tantalum arsenide in a way that normal linear optical absorption is not. Okay, so it's not as nice of measuring, integrals of Berry curvature, you're not measuring E squared over H, but nevertheless, you're sensitive to these structures that we think are important in various ways. Nonlinearity, Chi2 nonlinearities are only present in materials that have bioelectric dipole interactions, or only present in materials which break inversion, so they're non-centrosymmetric. And so this is some data from Dave Shea's group when Luyan Zhao, who's now in Michigan, was a postdoc there. I was fortunate to collaborate with them on this. And what they had found in this YBCO, high temperature superconductor, temperature versus doping, this is the famous kind of pseudo-gap line coming in. And what they found was that they and me, that as you come down in temperature, there is a line here which essentially parallels this line where other features are found of the pseudo-gap, where the second harmonic generation onsets in this fashion here. And so, I mean, I think this is something that, there's been a long-term debate about the pseudo-gap and the Coop rates. Is it a phase transition or is it a crossover? It's not clear with the large energy scale with the pseudo-gaps coming on. And I don't know if this is some people would call it epiphenomenon or not, but this data establishes definitively that there is a phase transition along this line. Right here, we don't know what its particular nature is, but it breaks inversion. The material doesn't break inversion above and breaks inversion below. Okay. So that's something that you can get out. This is a kind of thing that you might be able to see through other structural probes like X-ray diffraction, but this is a transition metal oxide. X-ray diffraction is notoriously difficult to see small distortions in the oxygen. X-rays aren't very sensitive to oxygen, and so it's techniques like this. Dave's group did work some years ago on iridates and found a similar, in a crystal structure that everybody thought was well understood in iridates, and found a similar onset of the second harmonic generation. And they then sent the X-ray crystallographers back, and they found that the space group of that system wasn't what was initially thought, because there were small distortions in the oxygens which had eluded the initial refinements. Yeah. Yeah, so in this experiment here, so that was a puzzle. Why does it exist at higher temperatures? But there are other nonlinearities which are possible. And in this case, it was thought to be the electric quadrupole response, which has no particular symmetry constraint on it. So at high temperatures, when they take data, they're kind of coming in with polarized light, and they're looking at the light that comes out in the S&P polarizations. You get these kind of flower-shaped patterns. And from that, it was consistent with electric quadrupole radiation at the high temperature regime. And then you come to lower temperatures, this flower shape changes, and it was consistent with electric dipole, SHG.
The title of the slide is the growth symmetry. Can you see actually here the symmetry break? The quantity is zero.
So there is, I would say, an element of model dependentness that what is happening up here at high temperatures is electric quadrupole. Yeah, Steve.
Yeah,
That's weird. Yeah, I agree. Yeah. Okay. Anything else? Okay, good. Okay, so that's all about Chi2 responses. What I want to talk about now, and for the duration of the lecture now, I'll get started on it, and then I'll have to continue tomorrow, is where we're going to use nonlinearities to tell us something about dynamical information about systems, right? So this is a technique called terahertz two-dimensional coherence spectroscopy. It's something that we've been pushing a lot in my group. I had some thoughts about this many, many years ago now. Read the technique of two-dimensional coherence spectroscopy is actually, the technique was invented, and I'll mention this, was invented in the context of nuclear magnetic resonance. So there you're using radio frequencies to interrogate and manipulate nuclei. Then physical chemists got involved with the same general ideas, looking at vibrations and bonds at much higher frequencies. And now, finally, us physicists can work on this, where we can use, people in condensed matter physics, where we can use terahertz radiation at the millieV scale to do similar kinds of things and get, again, unique information out. Let me give you a cartoon of what's happening here. So let's imagine, as a thought experiment, we're going to imagine driving some system with two pulses, okay? We're going to call them A and B. And there's a bunch of oscillations here. I can separate them in time, and I can run A and B through the sample. And I can imagine doing an experiment with A and B together A by itself and B also by itself. And I can look at the difference here. Let's say the E and L, these are all signals that kind of appear in my detector. And again, I can imagine doing it with both pulses together, one just by itself and the other is by itself. If the system was purely harmonic, I would get 0 out, right? That's what happens when waves are harmonic. They don't they don't affect each other at all, right? So imagine then, though, that I'm dealing with 2 weakly nonlinear oscillators. I can imagine them, let's say, charged pendula that I'm driving in this particular fashion. And I'm going to make a 2-dimensional plot. This is 2 frequency dimensions here, and this is the 2D of 2-dimensional coherent spectroscopy. And I'm going to plot this nonlinear response out of the board, right? So this guy has one frequency and that has the other frequency. And what I'll see is that I get, by a feature of a nonlinear oscillator, is that if I pump it at its frequency shifts a little bit. And so I can tell that I've already pumped it when I come back and I probe it later. And so I could pump here and probe there and pump here and probe there, and I will get these 2 responses. But if I pump here and probe there, I get nothing, right, along there. Very roughly speaking, the projection on the probe frequency axis here, that very roughly speaking, that projection is the linear response. Okay, so that would be the situation with 2 independent oscillators. Imagine I take these guys and I kind of weakly couple them together in some fashion. Now, what would happen with a linear response? Well, the linear response, if I can imagine I couple them, the 2 oscillators, they could shift, they could broaden, perhaps they become asymmetric. If I had a good enough theory, I could perhaps model it and understand something about it, but I seldom have good enough theory. But in the nonlinear response, that's not what happens. You get these off-diagonal peaks where nothing existed before. And at some level, this is nothing more complicated as I can go in and I can shake the green guy and I can make the red guy move, right? But it's not a matter of having a good enough theory. Again, these things might broaden or shift a little bit. But here in the nonlinear response, it's a matter of off-diagonal peaks appearing where they weren't before. Okay, so that's one thing I can imagine doing. I can also imagine a situation where I maybe have many weakly nonlinear oscillators in this fashion, and so many, and the frequencies are kind of all congested. The linear response is just this big blob here. Those oscillators might have very long lifetimes, very sharp spectral peaks, each of them, but I can't resolve them because in the linear response, there's just this big blob. But I can imagine with this streak along the diagonal, I could go through and take an anti-diagonal cut here and resolve the lifetimes in this fashion. So that's the basic idea. And as I mentioned, this was discovered, first exploited in the context of nuclear magnetic resonance, and still it's called multidimensional NMR, or 2-dimensional NMR if the dimensions are 2. 2 Nobel Prizes have been given for doing NMR, 2-dimensional, multidimensional NMR. I think the structure of the blood protein myoglobin was first worked out in this way. And then these are even worse units, chemical shift in ppms. I have no idea what it is. That's frequency in something in the radio frequency range. And that's also frequency. This is of the 2-dimensional spectrum of codeine, right? Which is anesthetic. That's the diagonal here. And those are the linear responses. And so what you can see is there's these off-diagonal peaks, and what happens is these all correspond to nuclear resonances, and when 2 nuclei are close to each other, they dipole couple, and you can work out by the intensity of this peak, you can work out how close they are to each other because the dipolar couplings have a well-defined form, right? So it's complicated, but nevertheless, some of the cross peaks don't exist, and there things are presumably really far apart from each other, and sometimes they're intense and they're closer, and you can work out structure in this fashion. And this is what chemists and various kinds of biochemists do with this technique all the time. We are doing, that's not so relevant for what we want to do. We want to think about experiments, let's say on the tens of degree Kelvin. So that's going to be terahertz frequencies, hundreds of gigahertz. That's what an experiment looks like. There, kind of schematically, that is, I was asked earlier about lasers. So that's an amplified laser system, much, much more intense than the lasers that we were using for the linear response spectroscopy. The lasers come in, go through a series of beam splitters, hit this nonlinear optic crystal in a particular fashion. The beams are combined. This is laser here. This green here, now that's terahertz. Focus through the sample, come back, and is detected in various different ways. So this generation detection scheme is very different than the kind of terahertz I was talking about earlier, but the pulses don't look that different, right? One of them by itself, this is, again, the electric field as a function of time in picoseconds, and so it's roughly the same. It's about a picosecond long, but you can see now we're thinking about electric fields which are much larger, hundreds of kilovolts, Okay, so this beam here split into two, the laser, so I could generate two pulses, and those are the two pulses there. That's what data looks like, and I'm doing this procedure I talked about earlier. I do an experiment with A, or I don't do any experiments. Will, for instance, does these experiments. I do an experiment with A. Will does the experiment with B. He does the experiment with A and B together, and then looks at the difference, and the difference is the nonlinearity. That's in the time domain, but we can look in the frequency domain. Yeah, okay, I'll take five more minutes. Yeah. Okay, so question, what can we learn? Well, it's complicated. We need to be clever, and we need to kind of, we can't just address and kind of do experiments, just plunk things into the beam and see what comes out. We need to think kind of cleverly about what the kind of information we can access. Let me talk a little bit about the complication first, and then we can now start to make sense of it. So if that's the classical electric field that we're driving the system, and this is the nonlinear polarization that we develop. Again, we can imagine doing an experiment here instead of A and B, I'm calling them fields J and I. And I can imagine doing an experiment with one or the other, or then both together. And so I can plug this electric field into this kind of form of the susceptibility, and I can multiply it out. Oh, geez, that's a lot. And that looks like a big mess. It's not quite as bad because, of course, it's a real physical response. And so everything's coming in complex conjugate pairs, right? So that's one, okay, not quite as bad. Now, when I look at it a little closer, I can see I've kept track of the exponents up here. And I see that there's a particular frequency structure here. So this guy here is like 2 omega j plus omega k. This one here is omega j minus omega j plus omega k, right? So these all correspond to different physical processes, different interactions of the system with the light pulses in different orders. It's a chi-3 susceptibility, but I'm using 2 light pulses, and so I have 2 powers, the first field and 1 of the second, or 1 of the first and 2 of the second, but they can appear and come in different combinations of different complex conjugate pairs. And again, they correspond to different physical processes. So this one here, that's maybe the most straightforward to understand. That's the third harmonic generation. If I imagine I'm using a reasonably monochromatic beam, and I have this thing, I'm going to get an oscillation which is 3 times the driving frequency. This one here is also perhaps intuitive to understand. It's coming in like E star, right? Omega j minus omega j times E. And E star, that's an intensity, right? So what I can imagine, this what we call pump probe signal, this is a process which corresponds, if you will, to absorbing using quantum language, absorbing a photon, and then having the system in this like low energy, slightly non-equilibrium situation. We don't like to use the language of non-equilibrium here. We want to use the language of nonlinear optics, but that's kind of is an okay way of thinking about it. We have absorb a photon, and then we have the system in this slightly excited state, and we're going to probe it at some later time with another photon here, which has a frequency omega k. There are other ones as well. We could talk about a 2 quantum signal. There's this one here, which is I labeled R, the rephasing response. If you're familiar with the language of spin echo or photon echo in the context of like an NMR, this is called the Hahn sequence, is the most famous way of getting this. That we don't usually use in NMR the language of perturbative interactions of light with matter, but if you were, that's the one that has the analog there, which is essentially the spin echo peak. Okay, and it's going to be very, very useful for us. Okay, all of this stuff all together, you might think again, it's just a big mess. But this is where the 2D of 2D frequencies come out here, right? So this is a plot of data on yttrium ferrite, which is a canted antiferromagnet. It has a number of different magnetic modes in it, which go by, they have different symmetries. That's not particularly important for this discussion now, but this is what data looks like in the time domain. So that's this interpulse delay. That is the kind of the oscillation in the lab. We look at the Fourier transform of this, and this is this 2D spectrum here. Yeah, there's some kind of excitation frequency that runs over positive and negative frequencies, and then we call the detection frequency. Those different responses that I referred to, pump probe, rephasing, 2 quantum, they all appear at different places in this plot. Okay, so I can, by using what we refer to as the frequency vector scheme, look to see where these spectral responses are, and then identify them with the particular process that generated them. Okay. So that one here corresponds to 1 factor of minus omega j and 2 positive factors of omega k. So this is the conjugated field of the pump and then 2 powers of the probe. That's what's called the 2 quantum signal. So in this system with magnons, this corresponds to exciting the system twice. So the system is in a 2 magnon state, and then letting it decay to a state that radiates here. And so what you would be sensitive to here, you could, for instance, be sensitive to intermagnon interactions, right? It's because you could find that this state here was at slightly different frequencies than a single magnon state, right? The 2 quantum state, if there was like a bound state or something. Oh, I'm almost done with this part. That guy there, that's the pump probe response, okay? So I'm going to talk tomorrow about metals. And in metals, this rephasing structure, 2Q structure, 0 frequency oscillations on the Fermi surface, none of that, these kind of finite frequency oscillations aren't important, but the pump probe response is important. And I'm going to argue that polarization sensitivity is very important with getting unique information about relaxation processes in metals in a way that you just can't do otherwise. That guy there is, we talked about Chi2 processes, and we're sensitive to all the nonlinearities there. This is the second harmonic generation, that peak that would appear right there. So again, I can go through and, as a matter of I can make this particular plot, isolate the different peaks, and each of them carry information about different physical processes. It's complicated, right? But it comes, I hope to convince you, I'll hope to do that in the next lecture. It comes at the, it comes with the fact that we get to learn unique information that we can't get at the level of linear response. So as I said, if we're going to do complicated experiments, we should be doing them for good reasons. So I'll just stop there, and happy to take questions if there are. Yeah.